So I want to do this problem here. It's similar to what we'll see on the exam that's coming up in a couple of weeks, and I'll give you more information about the exam as it approaches. The problem is calculate the heat released when 68 grams of steam at 124 degrees is converted to water at minus 20 degrees. Okay, so you have water at 124 degrees C. And you're cooling it down to minus 20. Okay, you're cooling it down to minus 20 degrees C. So that's going to release heat to the surroundings. How much heat is being released to the surroundings? And this is 68 grams of steam. Okay, steam. Steam is nothing more than water. All right, so I'll give you the equations here. Okay, the equation is Q equals ms delta T. Q equals ms delta T. Q is our heat. S is a constant called specific heat. Okay, so you do not need to know the definition, but I'll give you the definition. It's the amount of heat required. I'll just use Q for heat, okay? Amount of heat required to raise the temperature of 1 gram of a substance by 1 degree C. All right, amount of heat required to raise the temperature of one gram of a substance by 1 degree C. So you got 1 gram, you want to raise that gram temperature by 1 degree C. This is called the specific heat. For our purposes, you do not need to know the definition. For our purposes, we just need to know the constant, right? So the constant for each of these, and they'll be given on any exam. You don't memorize constants in this class. So we have the three specific heats of water as a steam, as a liquid, and as a solid. Okay, so solid, liquid, and gas. Gas, they're calling it steam. Okay, what are our temperatures? Okay, our temperature is 124 degrees C, and our final temperature is minus 20 degrees C. 124 degrees C, cooling it down to minus 20 below zero. Okay, so I think some places in the Midwest have temperatures that go really down to minus 20. Okay, so every day is a snow day for them. All right, so we split this apart. Okay, we don't just plug it into this equation randomly. Okay, M is the mass, S is the specific heat, and delta T is the change in temperature, final minus initial. Okay, final temperature minus initial temperature. Okay, change in temperature. All right, so first thing we're going to do is we're going to break this problem down into its individual components. Okay, break this problem down into parts. We have 124 degrees C. Okay, we're cooling it to minus 20. Okay, we're cool some more until we reach here. Okay, until we reach 100 degrees C. Okay, that's our first step. Okay, so I'm going to call this Q1. We're going from 124 degrees C to 100 degrees C. Okay, let's calculate the Q1 for this. So this is going to be Q equals ms delta T. Okay, the mass is 68 grams of water. S is the specific heat. Let's use the specific heat of steam because from 124 to 100, water is gas or steam. So we're going to use this specific heat, which is 2.02. Notice the units, class joules over grams degrees C. Okay, those are the units of specific heat. It's a constant, and it'll be given to you. Okay. And then final minus initial. Our final temperature is 100 degrees C. Our initial temperature is 124 degrees C. Okay. So this is what we want to put in our calculator. And let's go ahead and do that. Okay. Calling this Q1. The grams cancel, degree C cancel. We're left with joules. So 68 times 2.02 times, what's 100 minus 124? Oops, couldn't see that. So, all right, 68 times 2.02 times, what's 100 minus 124? Okay, so I'm getting about minus 32, I'll just go 97 joules. So that's Q1 in going from 124 to 100 degrees. Okay, this is cooling. Okay, when you go from 124 to 100, it's cooling, and the Q will be negative. All right, in a different color pen, let's do the next thing here. All right, we've gone from 124 to 100. At 100, we have what's called a phase change. Okay, so what do you need to overcome at the phase change? As you cool, you need to overcome, or this cooling needs to overcome delta H vaporization. Okay, so Q2, we'll put it in blue ink. Q2 is the phase change. Right, so we got from 124 to 100, and at 100 we have a phase change. We have to overcome this as it cools. Okay, it's cooling. Now we're at this stage where it's got to cool all the way below 100. So it's got to overcome the phase change of both liquid and vapor. So this is how we'll do this. We have 68 grams of steam, which is water. Okay, 1 mole of water is about 18 grams of water. You know this? Okay, hydrogen is about 1.01. Oxygen is about 16.01. So we have so about 18.03, 18.04. Okay, you add the number in the periodic table, and hydrogen gets multiplied by 2. We'll go 18.04 grams of H2O. And we know that the delta H vaporization at the phase change, this energy is 40.79. I'll give you that number. Okay, this is just the energy required to overcome vaporization. It's 40.79 for water. Okay, so for every 1 mole, we have 40.79 kilojoules. Let's see here. Let's just convert this to kilojoules. That's okay with you. So to convert it to kilojoules, we'll divide by 1,000. So 1, 2, 3. So minus 3.2. Minus 3.30 kilojoules. Okay. Okay, so on the exam, it can be joules or kilojoules. It doesn't matter. Okay, unless they tell you joules or kilojoules. All right, and then 1 kilojoule is 1,000 joules. Okay, so this will be our Q2. Okay, so we have kilojoules or joules, and then we'll convert it to. That's fine. We don't need this. Okay, then we have our kilojoules here. Okay. So we'll do our kilojoules and kilojoules. Okay, we'll add everything up in kilojoules, or you can add everything up in joules. It doesn't matter. Joules or kilojoules. Make sure you add them up consistent units. All right, so 68 grams. Okay, the grams of H2O cancel with the grams. The moles cancels with moles. This is the delta H vaporization. So 68 times 40.79. Okay, divided by 18.04. And we have about 154 kilojoules. Okay, 154 kilojoules. All right, what's the sign on this? It's cooling. So what will be the sign? Okay, it will be negative. All right, it's not positive, it's negative. Okay, because it's cooling. Okay, on the exam, make sure it's cooling, you have a negative sign. Okay, the Q will be negative. All right, so that's Q2. This is the heat that's given off, 154. This is the heat given off, minus 3.30. Okay, we've overcome this. All right, and now what's our next thing? We're going from 100 to 0 degrees. So this will be Q3. 100 to 0 degrees, that's Q3. So we'll do that in red ink. So this is going to be from 100 degrees to 0 degrees. We're going to call this Q3. Okay, heat number 3. All right, so here we're going to use Q equals ms delta T. All right, our mass still is 68 grams. Our S, we'll use the S from 100 degrees to 0 degrees. Water is going to be liquid. Okay, so this is what we're going to use for Q3. All right, Q2 was the phase change, so this is Q3. 4.184 joules over grams degrees C. Final minus initial is delta T, and final is 0 degrees C. Initial is 100 degrees. Okay, 100 degrees. All right, the grams cancel, degree C cancel, and then we'll get this in joules, and we'll convert it to kilojoules. All right, so 68 times 4.184. 68 times 4.184, okay, times minus 100, okay, times minus 100, and this is minus 28,451 according to my calculator. Let's convert that to kilojoules because we converted the other ones to kilojoules. All right, we'll divide by 1,000 to get it to kilojoules, and that is 1, 2, 3. Okay, minus 24.5 kilojoules. Okay, so if you're rounding, I'm not going to take off points for rounding. This is going to be our Q3. All right, and now we've crossed this, which was phase change. We went from 100 to 0. What happens at 0? Okay, what happens is 0 is phase change, and that phase change this time is 6.01 kilojoules per mole. You do not have to know that number. I'll give it to you, but this is the energy for water to get it to melt. Okay, most of it's going to remove those hydrogen bonds. So now we'll do Q4. Q4, we're going to call that a phase change. And a phase change at 100 now for water. Now we have a phase change at 0 for water. We'll do that in blue ink. No, do that in black ink. Okay, we'll call this Q4. All right, so we have our 68 grams of steam, or water now. Now it's water. And the specific heat at 0 degrees, we're going to use the specific heat of water as a solid, which is about 2.06 joules over grams degree C. Okay, 2.06 joules over grams degree C. Because water is mostly a solid around this temperature. Okay, delta T here. I'm sorry. No, I'm so sorry. This is wrong. I'm giving you bad information. I'm a bad professor. I'm sorry. Okay, phase change at 0 degrees. All right, so it's going to be 68 grams of water. All right, 1 mole of water is how many grams of water? Around 18.04 grams of water. And 1 mole of water is, what's the energy? It's going to be about 6.01 kilojoules, okay? 6.01 kilojoules. This is what you're going to do at the phase change. All right, so erase, erase, erase. We'll keep it at kilojoules because all the other ones are at kilojoules. Okay, this is called delta H fusion. Alright, so cross this out. We don't do this. Okay, we do this at the phase change. All right, 68 times 6.01 divided by 18.04 22.7 kilojoules. We'll just go with that. Okay, 22.7 kilojoules. Don't forget. Okay, the grams cancel, the moles cancel. So I'm getting about 22.7 kilojoules. And this will be my Q4. 22.7 kilojoules. And what will the sign be? Negative. Okay, why is the sign negative? Because you're cooling, okay? The heat's coming out to the surroundings. So for cooling, like we did in the other phase change, for cooling the sign is a negative. Alright. Alright, now I got ahead of myself, but now we're at 0 degrees. Now we're at 0. And we'll go to our final temperature, and the final temperature is, what's our final temperature? Minus 20. Okay, this is going to be Q5. Okay, Q5. And what color should we use for that? I'll use this, whatever color this is called. Okay. So finally, we will go from 0 degrees to our final temperature, and as I said before, our final temperature is minus 20. Okay, this will be Q5. All right, now we'll do this. Q equals ms delta T. So our here is 68 grams. It's no longer steam once it's at, these temperatures in the cooling part. 68 grams is the mass. The specific heat, we'll use the specific heat of water as a solid because from 0 to minus 20 it's going to be a solid. And that's 2.06 joules over grams degree C. Right, what's our final temperature? Right, our final temperature is minus 20. What is our initial temperature? 0 degrees. Okay, so the grams cancel, degree C cancel. And what is this on our calculator? 68 times 2.06 times minus 20. Let's divide by 1,000 to get it to kilojoules. Is that okay? Okay. And that's minus 2.80 kilojoules. Okay, divided by 1,000 to get it to kilojoules. This will be minus 2.80 kilojoules. Okay, so like I said, joules or kilojoules, it don't matter to me, okay, for testing. Right, so what is our heat in going from 124 to minus 20? Okay, we will add, going from 124 to 100, that's Q1, which is minus 3.30 kilojoules. Okay, plus the phase change at 100. Okay, we got to get through this. Phase change at 100, which is minus 154 kilojoules. Okay, we've overcome the phase change at 100. And now we're going from 100 to 0 in the cooling part of the curve, which is minus 28.5 kilojoules. Plus minus, this is confusing, plus minus 20.85 kilojoules. Okay. We have a phase change at 0 degrees plus minus 22.7. And then finally from 0 in the problem we go to minus 20 plus Q5 plus minus 2.80 kilojoules. Okay, so these are the 5 heats we add that will give us the total heat. So it can be in joules or kilojoules, okay, don't matter. All right, minus 3.30. I can see this being, I can even mess up this up. The plus and minuses can mess you up. So minus 3.30 plus a minus 154 plus a minus 28.5 plus a minus 22.7. Did you get to minus 208.5? Anybody's doing it with me? I just need one person to verify. Okay. Well, anyways, just make sure on the exam you just be careful and double check your answer. Minus 208.5 kilojoules is what I'm getting. All right. Okay, don't forget the minus sign. Okay, adding all these 5 heats. All right, so can we do this on an exam? Okay, I'll give you the equation, I'll give you the constants, okay?
Did you add Q5 to that?
Maybe not. Oh, I did not add Q5, yes. Okay. Thank you, thank you. I saw you talking, so I was wondering, like, all right, minus 211.3. All right. All right, thank you so much. So can we do this on the exam? And unlike me, can we add all 5 heats properly? All right. What are the 2 phase changes going to be at? Where? At 0, and then where else? 100. Okay. If it's heating, what will the sign of Q be? Positive. If it's cooling, negative. That's just a convention that they thought up. This is just something you have to memorize. If it's negative, it's cooling. Anytime heat's given off, that thing that's giving off the heat becomes negative. What's positive? The same value but positive? The surroundings, okay, the universe. All right, so this problem, something like this will be on the exam. We'll talk more about this as the date of the exam approaches. All right, our last thing in chapter 11, and then we'll do a little, let's check our time situation here. We'll do a little thing here for starting chapter 12. The last things are phase diagrams. All right, so on the quiz, I have you draw a phase diagram. I probably won't ask you much on the test. If you read a textbook or go on the internet, you won't believe how much information there is on a phase diagram. It's like, wow, there's so much. I didn't even know this when I was taking chemistry. But let me tell you what I think is important. First of all, it's a graph. On the y-axis is the pressure. Okay. And on the x-axis is the temperature. Okay, so these are different pressure, temperature combinations. So at some pressure temperatures, you are a solid. At some pressure temperatures, you are a vapor, whatever XY coordinates. Some pressure temperatures, you are a liquid. And there are some pressure temperatures where you are all 3 states. Okay, and when you are all 3 states, that's called the triple point. Solid, liquid, and gas all coming together. Now here on the left, this is water. And then here on the right is actually CO2. Every phase diagram will be different for every substance. Okay? This I got from your book. All right, and there are some pressure temperature combos where you straddle the line between solid and liquid. And there are some pressure temperature combos where you straddle the line between liquid and gas. And then there's some pressure temperature combos where you straddle and you are essentially both a solid and a vapor. Okay? So that's really all I'll ask you for as a phase diagram. Now, something's very interesting about water. Okay, water is one of these most amazing substances. If you ever take higher level chemistry classes, there's a whole dedicated aspect to water. So the water, for water in the phase diagram, the solid liquid, you see that? It actually bends backwards. Okay, it bends backwards. Okay, no other substance has that. Okay? bends backwards like this. Okay, this bending backwards at the solid liquid phases is unique to water. Other substances are more going to be slanted forwards, right? Okay, either a little bit more straight or a little bit more clockwise. This is bending counterclockwise. So that's very strange for water. I don't say it's very strange. I say that's very unique to water, okay, given the remarkable properties of water for chemistry and biochemistry. Okay, so water has this weird backward bend for the solid liquid phases. And another thing I want to tell you, I do not know if you remember, but we had a graph, or maybe we did it because of the snow days. We have a graph where you have vapor pressure and temperature on the x-axis. Let me see if I can pull that up here in our notes. The graph of vapor pressure on the y-axis and the temperature on the x-axis, okay, it looks like this. Okay, it has this profile. Okay, for diethyl ether, for water, for mercury, and if you go at 1 atmosphere, this is the normal boiling point. Okay, normal boiling point. Okay, where the pressure on the outside is equal to the pressure of the liquid, it begins to boil. This is called normal. So 1 atmosphere is normal. Okay, drop it down to the temperature, that's the normal boiling point. Okay, so the curve, just look at the curve. How does the curve look like? Okay, it looks like this. Okay. Well, look at the phase diagram for this. Okay, liquid and vapor, it looks just like that. So it's exactly the same. If you graph vapor pressure versus temperature, it's going to have the same shape, same profile as the phase diagram, pressure, temperature, liquid and vapor, the two phases. Okay, so these are the same. And again, I just want to tell you guys, at 1 atmosphere pressure, okay, this is called the normal boiling point. Alright, so this is a wrap of chapter 11, and let's go ahead and move on to chapter 12 here. Alright, with your blessings, we will do that. Alright, so our first chapter in Chem 2 is done, and we will worry about that for the test review whenever that comes before the test. All right, I thought I would take this chance for you guys to just relax and show you some very simple thing. It's nothing too extravagant or great, but I'm going to take a water. Okay, this is water from our lab. I'm just going to pour water in here. Okay. So there's water. I'll pour roughly the same amount of water here. Okay, roughly. And this water is what I'm going to call a solvent. How many of you have heard the term solvent? Can I get a show of hands? Solvent. Almost everybody has heard the term solvent here. And so what is a solvent? All right. Okay, go ahead. Right. Okay, a solvent, I'm going to call the dissolving medium. Okay, what you want to dissolve the thing in. Okay. Now, in this example, I just poured some water. Water is going to be the solvent. And if water is the solvent, we also call it aqueous. Okay, aqueous. Okay, aqua, aqueous. Aqua, aqueous. Okay? So water is going to be the dissolving medium. Can water be your solvent? Yes. Okay? Is excuse me, is water the only solvent ever? No. Many things can be the solvent. Good. Many things. It doesn't have to be water. Our body uses water as a solvent, but it does not have to be water. Your solvent can be, I don't know, ether, ethanol, whatever. Okay? But if it's your solvent is water, it's usually called aqueous. All right, I'm going to add some glucose here. This is glucose powder that I got from the store on this separate beaker. Okay, so I'll just add whatever. Okay, I'm making sugar water here. Okay. You guys do this in the kitchen, and you probably do it better because you have teaspoon, tablespoon, or whatever it is. Okay. All right. So I added in this separate beaker a couple of tablespoons, or maybe teaspoons of sugar, okay, glucose. Okay. Have you guys heard the term solute? How many of you, if I can see a show of hands, how many of you have heard the term solute? All right. So we're going to call this powder of glucose, we're going to call it the solute. Okay, what do you think solute means? That's correct, okay? It's the particulate that you want to dissolve, or the thing that's being dissolved, all right? I'll call it particulate, okay? Instead of thing being dissolved, I'll call it particulate being dissolved. That is being dissolved into the dissolving medium. So is our solute always glucose? Obviously, you could have salt, you could have whatever you get from the grocery store, anything that's a powder, vitamin C powder, whatever, okay? It just so happens if our solute is in our solvent of water, then it's aqueous. Now, is this soluble? What do you think, yes or no? If I switch these around, could you tell which is which? Okay, I think they're indistinguishable. So they are. So glucose is soluble. Okay, are all solutes soluble in water? No. Oil, which is a liquid, doesn't go into water. I'm sure we can find something in our lab. You can find a solute that doesn't go into water. That's called insoluble. But here, glucose is soluble in water to an extent. If I dump this whole thing, obviously it's not going to be, it will be insoluble. So what I produce now is water here, which is solvent. This is solvent plus solute. I've produced a solution because it went in, it dissolved. So we've made a solution. So the first thing I want you guys to know is that a solution is equal to solvent plus solute. Okay, so let's write that down. Solution is going to equal to solvent plus solute. We want to keep our mind aware of this. Okay. It just so happens because the solvent is water, we're going to call this an aqueous solution. Okay, aqueous solution. If it dissolves, which it did, and the solvent is water, which it is, we're going to call it not just any solution, we'll call it an aqueous solution. Okay. All right. So these things, as you guys mentioned, are indistinguishable, right? This is water, and this is the sugar water. Okay, I think, right? Yeah. So, are these one and the same? No. Okay, obviously, one has sugar. This one probably tastes sweet. This one doesn't taste the same. But we don't taste anything in the lab. But what we can do is look at what's the difference between solvent and solute plus solvent. Okay, so what's the difference? Let me ask you this. What is the boiling point of this water? Boiling point? In degrees C, what does water boil? Okay, so this water is going to boil at 100 degrees, right? 100 degrees C. That water is going to boil at 100 degrees. What will this boil at? Same 100 degrees? Higher or lower? Or the same? Okay. So, if you add a little bit of solute to a solvent, the boiling point will it stay the same? It will not stay the same. The question is, will it go higher or lower? Okay, you have more molecules, more intermolecular forces to overcome, so will the boiling point be higher or lower? Okay, so the first thing that happens is that you add a solute to a solvent, the boiling point is going to elevate. All right, so we have what's called boiling point elevation. Boiling point elevation. Okay, the minute I add a solute, if I add a lot, as long as it's dissolved, or I add a little, or I add one speck, if I add one, atom, okay, however little or however much I add, as long as it's dissolved, my boiling point will go up. This is called boiling point elevation. Okay. The second thing that will happen the minute I add a solute, whether I add a lot, a little, or just a speck, as long as it's dissolved, as long as it goes into solution, my freezing point will go down. This is called freezing point depression. The minute I add a solute. Excuse me. The minute I add a solute, my freezing point will go down. The minute I add a solute to the solvent, my boiling point will go up. Okay. What will happen to my vapor pressure? Will it go higher or lower? Or will it stay the same? Okay, well, it's not going to stay the same. The question is, will it go higher or lower? Okay, more molecules, more intermolecular forces. When you add this to that to overcome, will it become harder or easier to become a vapor? Harder. So does that mean we'll have more vapor or less vapor? Vapor pressure would lower. The minute you add a solute to a solvent. Okay, the final thing here is any biology majors. Okay, a lot of biology majors, maybe the pre-meds. One of the things that will also happen is that the minute you add a solute to a solvent is that you'll have osmotic pressure in the presence of a semi-permeable membrane. In the presence like your plasma membrane for those cell biology people, cell biology majors, in a semi-permeable membrane. Okay, this osmotic pressure for some strange reason has the abbreviation pi. All right, so the minute you add a solute like glucose to solvent like water, you make an aqueous solution as long as it dissolves. You can't just dump the whole thing in. And then four things happen. The boiling point is new and it's higher. The freezing point is new, it's lower. The vapor pressure is new and it's lower. It's more intermolecular forces. And if you happen to put a membrane there, you have what's called osmotic pressure or osmosis. Okay, begins to happen. So all of these four are what are called colligative properties. Colligative properties. Okay, so no matter how complicated the molecule, this can be glucose, which has some structure, some formula. This could be some poison. This could be an elixir. This could be the hardest chemical complex in the world. This could be the simplest chemical formula in the world. It doesn't matter the structure. It doesn't matter the molecular weight, as long as it dissolves in the solvent that you choose, as long as it dissolves in the solvent system, all four things will happen. That is the meaning of the term colligative. Okay, that's the meaning of the term colligative. No matter how complicated the structure is, no matter its molecular weight, no matter how simple, anything, as long as it dissolves into your solvent system, all four of these things will happen. Okay, that's the meaning of the word colligative. All right, so we'll do some problems like this in Chapter 12. And another thing we'll do in Chapter 12, which will start on Wednesday, is we'll talk about like dissolves like. Okay, so that will be for Wednesday. And I think we have lab on today at 2 o'clock, so I'll see you in the lab. I'll try to start it a little early if you want to get in there and come out. So I'll try to start at 1:45. I'll try, but definitely I'll be there at 2 o'clock, okay, which is the assigned time.